Hello, everyone. I'm Seogi. As organizer said, I'm going to talk about accelerating the use of public geophysical data for recharging California's groundwater. I'm Seogi. I'm a postdoc at Stanford Environmental Geophysics Group. I'm a computational geophysicist using various types of data, sensor data, ground, airborne, satellite. The other talk was basically talking about the satellite data, but there are whole different forms of sensor data, which I'm going to kind of touch upon. I'm really passionate about the open science, including software, documentation, data, as probably the most of the people like here. I'm really interested in extracting useful information from the sensor data to advance groundwater science and management. So a lot of the talk here, I guess it's more like a top-down approach, really talking about the Python packages and how that can sort of benefit other people. I'm going to step back and then go a little bit different approach, like a sort of the bottom-up approach. So I'm not going to, this will be the least like a technical talk throughout this SciPy conference, so be relaxed and then enjoy. But sort of the high-level question that I want to address here, I'm a researcher, and then we develop research knowledge, research tools, software, data. Then, and how do we turn that into a form or more tangible form that can be consumed by practitioners? And then particularly, we want to guide and provide guiding information for their decision making for specific problem. And I want to focus on the how do we utilize the public sensor data, which Shinseng sort of touched upon. And that's sort of the goal of this talk. And then I want to, like what I would probably show is not necessarily the best approach, but I want to share what we've done, and there are probably some insight that you could potentially learn from this talk. Okay, so speaking of the groundwater, believe it or not, groundwater occupies 97% or more of all liquid form of fresh water. So this is very, very important resource. You probably have seen like this type of picture, but the groundwater fills in the pore space. It's like an empty space of the rocks and sediments, like this image. If you zoom in at certain part of the subsurface, that looks like that. So if you then tie the water with the blue color, that would look like this, and then that's the rock matrix. Okay. And so 97%, it's a large volume of water. So it sounds like, oh, that's enough for us, but it's a finite volume. So with the population growth and climate change, the demand of the water can drastically increase. So what that means, for instance, if you think about the droughts, the last summer, there was a severe drought in the US, especially in California, but many other parts of the US. With that, you've probably seen some of the news articles about lake mats showing the bottom, and then that could show some scary things. What that means, you have no surface water. And that kind of induces more pumping of the groundwater because your needs about the water doesn't really change. And that could really threaten groundwater sustainability at global scale, not just in the US, but many parts of the world. So that's a very serious problem. And today I'm going to focus on California, especially the Central Valley, where this groundwater issues is very, very serious. Not sure if you've been there, but that's the satellite picture of the Central Valley, and that's the white boundary here. And it's bounded by Sierra Nevada, big mountains, and then west side, the Pacific Ocean. That's the Stanford Bay Area. That's where I'm coming from. Very nice area. And the bottom line here, the Central Valley is one of a very productive farmland, which to maintain that agricultural productivity, uses a significant amount of surface water as well as groundwater. And the severe droughts happened in California between 2012 and 16. Drastically increased that water demand that I mentioned. So people pumped a lot of water, right? So that really threatened the groundwater sustainability. With that, California government legislated what's called Sustainable Groundwater Management Act, called SGMA, in 2014. With that legislation, each local water agencies need to come up with what's called sustainability plan. And then if they fail, government actually steps in. And that's the situation nobody wants. And that kind of shows the pressure and the stress, the water issues in California. Okay. And just to give you a sense of how much water we're losing in Central Valley, it's about 30 cubic kilometer of water per year. And you probably have no sense what's 3 cubic kilometer per year. So for the past decade, it's about 30 cubic kilometer. And I didn't have really a sense of how much of that water is. So if you think about the reservoir, so Shasta Reservoir is one of the biggest reservoir in California. The capacity of that reservoir is about 6 cubic kilometer, and that's 5 times of it. So that's the amount of water that we're losing for the past decade. So that kind of like clearly shows the water out due to the pumping is way, way larger than water in due to the natural recharge. What the natural recharge means, like if there's a rainfall that percolates through the ground and hits the water table, that's sort of what we call natural recharge, and that's way less. And that's the critical problem that we're up against. And if you live around this region, either LA or California, it's something that you can feel it on your skins. If you actually drive over the Central Valley, those are sort of the scenery that you could see. So the farmers say, oh, there's no water for irrigation, or that's so expensive. So sometimes it's very, very expensive. So almond trees, like if you like the almond or whatever, pistachio, all of them are coming from Central Valley. And they're actually ripping out the trees because it's not financially feasible. And that's sort of the level of the problem. And so there's an urgent need for recharging California's groundwater, and what's called flood-managed aquifer recharge. It's one of the promising techniques the community is planning to implement quickly. And the idea is pretty simple. Whenever you have a surplus of water, and then your reservoir will be filled with lots of water, then in such a case, you can divert that water and then basically flood whatever the available lands. And if you think about the last winter, there was lots of storms. I'm not sure you've heard about atmospheric river. This is one form that can make a lot of precipitation in a short amount of time. Then you have lots of water available to be flooded in many types of different lands. And so that's good. And this technique is nicely aligned with the kind of the existing climate change or coming climate change, which generates more extreme weather events like floods. So with more floods, we'll have more water that can be captured in using this flood mar technique. And that led us to prepare the drought period, the period when we would use more amount of groundwater. So that's like a nicely aligned, kind of optimized technique. But the problem is we really need to implement this flood mar in many, many places quickly, because this problem is very, very serious. Okay? And there are many other challenges. We're going to touch upon one piece of challenge. We really need to locate the relevant recharge site rapidly. And here's an idea. And then so the missing data is about the subsurface. So think about like if you pour the water here, flood the water here, and then it'll go through what's called permeable pathway. So sand, if you think of sand and gravel, it's a coarse-grained, large-size grain size, and then it could be a conduit of the flow, right? So the water will go through, but then if you think about the clay, it's a fine-grained material. It's a barrier of the flow, so it'll block the water flow. So the water will go through like this and then hit the water table, and that's what we kind of can call a successful recharge event. But if you pour the water here, where the clay is presenting, then water will pond, and it could like just evaporate, or it could make a harmful effect for your crops. If you're like growing almond trees, that could like that could ruin your roots. So that's not something that what you want. So that's sort of the problem. And the general challenge here, we actually don't know what's the subsurface look like. And think about even below your ground, we don't know what it is, and it's hard to see, right? So that's the general challenge. And the challenge is actually the scale of this problem is large. If you think about the size of the water basin, it's about 50 kilometer by 50 kilometer area. So just thinking about even running around that area by yourself, it's still hard. But you need to see from surface to tens of meter or hundreds of meter depth to image the subsurface. So that's the general challenge we're up against. And in such a case, like electromagnetic imaging, EM imaging, which that's my research area, that's what I'm studying, that could be very, very useful. So the idea is somewhat simple. Like say you have a loop like this, then you inject the current, and back to physics 101, that's Ampere's law. With the Ampere's law, there will be a magnetic field generated. And then with the Lenz's law, there will be an induced current generated in the subsurface. And then that'll interact with the properties of like electrical resistivity, electrical properties of the subsurface. And it can generate the signals from the surface that can be measured at the receiver location here. That's the data that we're measuring, and it senses information about the electrical property of the subsurface, and you can actually do it on an airborne platform or the grounded platform. Okay? And those are sort of the detailed specs of what you can see or not. But the bottom line here, like this airborne method could be useful for basin scale. It's about size about a 50 kilometer by 50 kilometer area. And it only takes about a few days to map out that entire area. And the local scale TODM, it's the size of the farm. And it could be about like 800 meter by kilometer area. Again, it only takes a few days to map out that area. Both of them are large, and then the set of the questions that you're asking for your specific application might be different, and that gives you a bit of different information at different scale. And what we're imaging is the electrical resistivity, but what we want to see is the hydrogeology, like the sediment types. What is the grain size of the materials, and what is it permeable or not? So it's really important to understand what is the relationship between resistivity and the hydrogeology. So here's like it's a simple diagram starting from the lower resistivity end. Salt water, if you think about it, there are lots of ions, so it can conduct the current really, really well. The clays have a specific structure that can conduct the current really, really well, but that's a barrier of the flow in terms of hydraulic sense. Sand and gravel, it's an aquifer material that can be a conduit of the flow, but the important thing, their resistivity values are different. So by knowing resistivity value, you can infer what is the hydrogeology of the subsurface. That's the important part. But the fundamental challenge here, if you say you have a single resistivity value, but it's hard to determine what is clays or sand and gravel, because we're not directly measuring. It's an indirect measurement. So there's a need to build a correlation between this geophysical property, and if you have an in situ measurement, like for instance, if you drill a well, then you can actually build a correlation between your geophysical property or direct property that you want to see. Okay? So that's sort of where we're going. And here's a kind of example diagram that you can actually obtain from this airborne survey. So this is in Northern California. If you're familiar with the Sacramento River, that's where the Sacramento River is. It's about 30 kilometer or 50 kilometer area. And we're seeing from surface to a depth of 400 meter. And that's only taken about a few days to get this types of image. And that's the power. And the blue color here means the fine-grained, lower resistivity clay silt. And red color means coarse-grained sand and gravel. So if you think about the recharge, this is probably a good location because like it's surfacing exposed here, and then it can go all the way to the depth. So if you pour the water will go through and then recharge this deeper part of the aquifer. So that's sort of the level of information that you can get from this data. And then in a local scale, now we're at zooming into about 800 meter by 400 meter region using the ground-based technique. And then similarly, you can think of, there could be a pathway. If you pour the water here, they can hit the water table. Okay. So that's sort of the idea. So that's the pathline that what we're looking for. Okay. And here's a simple workflow that we developed. Okay. If you have a resistivity, three-dimensional resistivity model, then we build, if you have an in situ data from a wells, then you're going to build a correlation between resistivity and the hydrogeology. And then you're going to transform that into a form of a specific form of hydrogeology, which is in this case a coarse fraction. And if you think about for practitioners, like if you provide 3D image, if you have worked on 3D visualization, it's always very unintuitive and hard. So we need to turn that into a much simpler form that can guide their information. So what we're doing, we're generating what we call recharge evaluation matrix, which is a 2D map, then that can actually guide practitioners where they can sort of think about designing their recharge activities. So here, green, I'm going to use that color scale for good. And this, like a key knowledge of tool is published with few papers, but and actually we wrote an open source package that could do this sort of workflow. But yet the tool is not accessible or usable for people who are facing. Maybe those like the crews are like yourself, like it's okay. But for practitioners that I am working with, it's a big barrier. They cannot either they cannot do it or they don't have time to do it. They're not really kind of motivated to actually learn these types of skills. So that's the problem. And the geophysical data, EM geophysical data, are publicly available with some statewide airborne EM project. In this case, it's CDWR, means California Department of Water Resources. And that's like a green lines basically shows the flight lines they have flown over. And it's basically covering the entire Central Valley of California. It's about $13 million project covering about 25,000 light kilometer data. So it's a lot of data. But if you actually go to their open data portal, download, and that's how it looks like. It's all a whole bunch of zip files. So, and if you understand the data structure and then what they provide, it's okay, but yet it's not readily accessible, especially for practitioners. So that's our motivation. We want to make that ease of the process. We want to develop the web application that provides an easy access to this EM geophysical data, as well as the data analytics developed by researchers, scientific researchers, to generate this map of recharge areas. So that's our motivation. It's two wings. I'm not going to talk about much, but the developing web application, and we also develop educational resources, because as you can imagine, there are a lot of details. So it's important to understand what are the fundamentals under the hood to get this map. Okay. And that's our Sustainability Accelerator project. It's a one-year project ending this August. So we're going to launch that app pretty soon. And some of the part, especially for developing a web application, it's way beyond the research scope of our group. So we're teaming up with the startup company called CurveNote. And their goal is somewhat aligned. They are developing online platform for scientific writing, but it's one step forward for them actually plugging in the scientific compute engine, because when you're writing, you have a lot of numerical result, and you want to plug in the scientific computing. So that's sort of our motivation to work with them. And then we're also working with, closely working with the partners from federal government agencies, local water agencies, to develop a very practical tool that could be useful for their life, especially for groundwater recharge. And here's a somewhat complicated kind of full picture of what we have developed and how we, showing how I interacted with the CurveNote people as a researcher to develop this practical tool. It's very complicated, but I'm gonna dive in a couple of parts. So this part, as a researcher, I'm fine actually writing a Python package. And that's sort of the level that I could work with. And then I'm also fine with okay, I can use the Jupyter Notebook or Jupyter widget to turn that into somewhat like a graphical user interface. Those are sort of the level that as a researcher, scientific researcher, I'm kind of comfortable. And that's what I've done. So, and then I've used basically all this amazing scientific Python packages. And that's sort of one thing that I've done. And also the database I had to put together, and that's as a researcher, I could do it. And what was really useful, it's a Redibus. It's an online database designed for scientific researchers. And check it out if you're coming from university. Sometimes they actually provide free licensing. And that's what I've done. And the other part, all the hard part, there were some questions, how do you maintain the server? How do you launch the Jupyter Hub? Because we need science computing engine, and we have a GIS layer that we want to launch. So those part was handled by this CurveNote people, the hard part. And I'm gonna show a quick demo. So this is, so that's the website. And then if you actually go, we're gonna launch this in about a month. And if you click Recharge Now, and then what we're going to see is the GIS layer. Let's see. Oh, cool. Okay, that's the, well, it's always, I'm all nervous. So this is the GIS layer that you could it's a pretty typical GIS layer that you can interact with. And I'm not sure if you've been to California, but this location, that's my typical example that I use. So you can actually lay over various types of GeoJSON file or shape files. And you need to click this location. This is actually called a quea as a basin. But if you actually, this is a location where the groundwater issue is really, really serious. So what we're doing, once you click that button, we're querying the database, and then basically getting the statistics about how many data points we have in terms of water level data, water quality data, or sediment type data. It's an in-situ sediment type data from the drillings. There are lots of data that you're downloading it. I'm not going to go to the details, but once you queried your data within the region, then we're launching, using the Jupyter Hub to, I think we're using the Google computing machine. Then now we're moving to a server. And here, what we're doing, it's a bunch of Jupyter notebooks that we stitch it together. So this is the first notebook, which actually moves the data from the online database to the compute server. And we're basically it's loading the data, right? And then the next step will show, we'll start the scientific analysis or visualization relevant for this specific application. That's what we're going to do. Hopefully this will quick. Yeah, I'm not going to go to all the steps, but I want to show the second one. Okay, so this is the black dots. Let's get are the what I call electromagnetic data. So I'm going to show you. If I click it, it'll show the vertical section of electrical resistivity. So what you're seeing is the vertical section of the electrical resistivity. If you're familiar with this, is the Sierra Nevada, and then all big red is the bedrock coming in from the Sierras. And then all those yellowish color are likely sand and gravel, and blue could be the clays. So those are sort of the level of image that you would see at each line. And then the next step, and then there are many wells. So what we are doing from this geophysical data and then the sediment type data from in situ wells, we're building the statistical relationship. So the fine dominated, like a clay silt, will have a lower resistivity than the coarse grained material. So we have a two sort of like a distribution that we can build a mapping function from resistivity to a sediment type. And everything is happening on the Jupyter Hub, so it's running on the server. And you can generate the three-dimensional grid, and at the end, we're providing that recharge matrix in the form of 2D maps, and then you can export that in an accessible form to your GIS layer. So that's sort of kind of what we're doing. And then one more thing that I wanted to show is this is what like a sort of the miniature version, like a much simpler version of what you could do. So this is actually what the curve node product is. And this is a markdown, but you can actually embed output of your Jupyter lab or Jupyter notebook in the form of IPy, like IPy widget. Then what you could do, you can actually embed your widget into a documentation. And under the hood, we're running the Google server to launch that. But what it provides is an ability to it's an educational resources in this case, but under the hood, you can actually run a physical simulation and optimization and then show how we can actually do this process. So I'll quickly show what's called inversion. So this is actually the first step, how we're getting the image of resistivity. And anyway, okay, back to. So the web application will be available in 15th August. And that's the launch date for us. And the database is available, publicly available. If research codes are available, my slides are available through GitHub. And so what I kind of wanted to talk about today was how do we really accelerate the research knowledge into an action? And what was our experience to work with kind of the software engineering researchers together in the form that could readily communicate and then generate a product that could be really useful for practitioners. And I think this is a kind of like a good example. And a lot of pieces that we have developed could be expanded. So if we're running into a different set of problem, I think it will be way, way faster at next time. And I have huge thanks to CurveNode team to help us to finish this project. And thank you very much.
Thank you so much. At this point, we will go ahead and open up for questions. I see we've got one over here.
So yeah, I'm just curious from like a big picture, like water problem perspective. At this point, are you still data limited, or is it now you're past that and now you're in the hands of like, okay, we need to communicate the information we have to people who can actually like build pipes that will carry water to the places where it needs to go?
That's a hard question, and I'm not sure that I am sort of like qualified to answer that, because like it's such a big problem. And if you think about the recharge problem, the first part of the problem is actually forecasting. So you need to forecast when you would have a surplus of water in a short amount of time, because that atmospheric river is coming in really, really quickly. I think we're not there. So, but then what I am handling is another set of problem. The subsurface is a big monster as well. And the limitation of what I've shown, the resolution is always like, it's not as good as like if you think about it vertically, compared to your in-situ data, is way poor. So I'm not sure we have, we're getting more data, but I'm not sure we have enough data. But I think it's going parallel. So we have some data, we need to work with it and then try to kind of utilize it and then maximize the value of it. I think that's where we're going, I guess.
All right, we have another question over here.
Yeah, that was a great talk. Thank you. My question is really about data flow, and I have this impression that you spin up a compute server and you move the data to that server. Is that right?
Right.
So a lot of us in this community have been thinking about moving compute to the data. So usually because our data sets are so big, you can't move them around.
Right.
So I was wondering if in your community you have these questions too, questions about analysis-ready data, which your zip files clearly are not.
Yeah, so I'm not sure, I think I'm not the expertise on that side, but I think in our case, what we have used was all the processed, like a second level data. The raw data could be really, really big, but we sort of put it in a form that are small enough that transferring is not a big deal. But I think if you're really dealing with large satellite data, tens of terabytes, I think what you have said is way better approach. But so I think there are different level of problems. Sometimes actually the data is not that big, but the structure of the data and then how to query the data is actually the challenge. I think that the challenge that we had was more on the latter side, I think.
It's very insightful. Thank you.
Any other questions? Let's see, we got one over here. Then I'll bounce over there.
Yeah, thank you for that very nice talk. So one of the things you mentioned is that as scientists, we have, kind of the abilities and skills to be able to do some of this analysis, like on the cloud locally. But when you are dealing with other stakeholders who don't necessarily have the time or the expertise, that this can become challenging. And so you showed that you're building this website that you're going to launch soon. It still seemed that what you were demoing for us was like somewhat technical. So are the stakeholders that you are personally working with people that still understand the science but don't necessarily have the programming skills? And I mean, this obviously differs stakeholder to stakeholder, but I'm just kind of curious about your particular experience here.
Yes, that's the major reason we're partnering with the partners. And then in each step, we have exposed our product to them and then asked what they would do. A lot of our water managers have no desire to run this. They're going to hire a consultant because actually they have no time and they don't have like a human power in their resources team. But what we're providing, I think, was our motivation to develop the educational materials. So with I think there's a Stanford system that generates the online course. So we actually generate the online course, and then the web application, like that small educational apps that I have shown, it's a part of that videos and then apps. So people can learn it, and then they have a certificate. So at least those people who have a certificate have a base knowledge that they could utilize this. So that's how we were approaching that problem.
I have a question. I think it starts there, but so do the management people, I'm imagining them getting like the green maps with the good.
Yeah.
And then is that what happens? And then what? So they look at the green maps, say where it's good. How do you get a bunch of water and then move it to there?
So there are many other things. So say one other important thing is what's the source, right? So if you have a reservoir, and then if they're flooding, you need some path, like either pipelines or canals that then you need to like divert that water to your place. So those are sort of the different level of problem. So what we're imagining, so once they output our products to their own GIS layer, there are a whole bunch of other information they're going to bring in. They're going to actually start designing. So this is actually a piece of the information, not fully integrated solution. So they're going to bring in a lot of other information and then actually design what they would like to do and then evaluate their approach.
What sort of time frame does that happen over? I was imagining like it's raining hard. Do we divert?
I think that needs to happen very short amount of time because there's a quote. We have only a couple of wet years in 20-year time span. So you have very small window that you can do this. So you need to be prepared. And that's why we're motivated to do this and accelerate this process.
Great, thank you so much.